function, this is Leontief or perfect complements. And you should know this based on the minimum. So Leontief will always have a minimum of something inside, always. And whenever you see a minimum, it's never going to be anything else, Leontief. And just to kind of remind you, I'm just doing this real quick, these indifference curves, they are L-shaped. So if like this is the axes for the different different x's, these are the indifference curves. Remember, these represent points that yield the same level of utility for this person. So on IC1, maybe all of these points give them, 100 units of utility. And maybe IC2, because we're going up, it's going to be higher, maybe it's 200. So every point gives them the same level of utility on that one curve. And as we get higher, we get more. Can we give me an example of two goods that might be represented with Leontief for perfect complement? So we know what complements are, we should. Remember, things that go together. But in this case, this is super extreme. We definitely 100% want them in a certain amount, like certain proportions. So I think I said last week, I was talking about like a coffee drink and shots of espresso to sugars. Now this person only drinks their coffee with that. They don't want like any different combinations or proportions. They definitely want a certain proportion. Another example might be left and right shoes, right? Like when you go to the store, you definitely want to buy them together. For the most part, everyone does. So these would be perfect complements, things that you want to have or buy together. Now I'm also going to ask this next question about the MRS, marginal rate of substitution, the slope of these indifference curves. Okay, let me do that. So MRS, slope of these indifference curves. Yeah, 20 seconds. I know we did this at the end of class last time. It is in the slides. Okay. So again, kind of a mixed results. The answer, though, is that there is none. So these Leontief preferences, these are actually not true functions in math. I don't know if you remember when you talked in like calculus, you did like Calc TNA or just Calc 1. You probably at first did a lot of stuff with like limits and things like that, finding if functions are like true functions, if they don't violate a lot of problems or a lot of different things. This violates like the idea of functions in math because of this, vertical part here. So we actually can't take a derivative, which is what the MRS, is. It's a ratio of derivatives. We can't take derivatives here. And so there is none. You can say, might, have to answer NA or that it's undefined. In your notebook, it might be good to write down Leontief always has the minimum, always, and the MRS is undefined. So in the future on a quiz, I might say, oh, here's this utility function like this up here. What is the MRS? Without even thinking, or, really looking through your notes and everything, if you have it on top, oh, this is undefined. I don't need to do any kind of math. I don't need to divide by anything. It's just undefined. And it should be automatic, okay? Another one. So again, we only did 2 so far, 2 of these preferences. Next one is going to be 1.6 x1 plus 3.2 x2. And I'm going to ask you what type of utility function or preferences this represents. Type of preferences. Now 10 more seconds. Okay. This time the majority did get it. This is a linear function. So we've only really talked in this chapter about either linear or Leontief, perfect subs or perfect complements. So that was the only 2 you should be answering right now. But this is linear. First of all, because we have a plus, something plus something else, and there's no squares or exponents, there's no square roots or anything like x1 and x2 being multiplied. They're separate and they have something in front, but they're being added. That is always linear. So this is linear or perfect substitutes. And here, the indifference curves look something like this. So there's straight lines that go through the axes. Again, they represent different levels of utility. So this is like a 1 indifference curve, and it might give 50 units of utility. And the second might be 75, because as we go up, remember, utility always increases. So they represent all of these points on the line giving so much utility to this person. So every point here yields utility equal to 50. And up here, every point is 75. So perfect substitutes. Can anybody think of an example of perfect substitute? Okay, so perfect substitutes, these linear preferences, those are going to be goods that we can use in place of one another, like 100%. So again, it's an extreme case. A lot of times when we're thinking about like substitutes, it's not perfect. Like we might prefer one over the other a little bit, but these would be absolutely perfect that you can use in place of one another. So like x1 here, since it has this like lower coefficient, this might be, say, a 1.5, I don't want to do that, I'm sorry. Yeah, we'll do 1.5 liter of wine. Now x2, what we're saying is we can basically replace x1 as long as we have 3.2 x2. It's 2 times the amount. So this might be a 750 milliliter bottle of wine. X2 is basically 1/2 of x1, where, you know, maybe it's the same type of wine. We can buy 2 x2s and get, you know, basically the same amount of 1 x1. Don't need to know these numbers too much, it's not important, but we can use them in place of one another perfectly. We don't really prefer one or the other, we like them equally, just maybe different amounts that we need. Okay, so looking at this, I'm going to ask you again for the MRS, marginal rate of substitution here. Looking for this MRS. Might remind you it's the slope of these indifference curves, might help. Oh, 10 more seconds. Okay, good. Majority said 0.5, and that is correct. So slope of these indifference curves. And we had that formula for MRS is the marginal utilities over each other. But we also had a trick. This MRS just equaled this letter A, which is the coefficient on x1, over B, the coefficient on x2. So you don't really have to do too much calculation. You don't have to do derivatives here. If you remember this, all you do is take 1.6 and divide it by 3.2, which is 1/2 or 0.5. So again, this is representing the slope of all of these indifference curves. They have the same slope and they're parallel to one another. So the slope is constant. And this MRS is how willing we are to really trade between these two goods. You know, how much of one we're willing to give up of the other. That's what we're looking at.
Professor, I have a question.
Sure.
Should an MRS always be negative, or is there something else?
Yeah, that's right, Jason. Good. So because these are downward sloping lines, we do have to add a negative here. So good. It's just always negative. Sometimes I may not put a negative at all, just because that's how your book does it. But it should definitely be negative. If you see in like a quiz that none of them are negative, it's just assume that they should be. That makes sense to you. Later on, we kind of ignore the negative sign, and that's why your book ignores it. So I kind of follow them and do my own thing. But you're right, it should be negative. These are downward sloping lines. Okay. So we talked about the first two types of preferences, these linear and Leontief. Now we have another one, this third type. Now this third type, we're really not going to talk about too much. I'm going to mention it and I'm going to show you the functional form, and I might have like some questions about it, but we're not really going to do too many examples with it. These are known as quasi-linear preferences. So we have a function of, utility where it looks kind of linear. We have x1 plus x2, but there's some non-linear part, like a square root here. So that's why it's somewhat linear, quasi-linear, but there's a non-linear portion on one part, on one x. So this might be square root of x1 plus x2, like we just saw. It might be x1 to the 0.5, or well, a different number, 0.3 plus 3x2. So again, there's some either exponent, like the square root, it could be a natural log also, so ln x1 plus x2, something like that. But this is being added to a linear portion. For this, I'm not even going to ask for the MRS. The MRS isn't too hard to find, but I'm just not going to ask you for it. But you might need to identify that these are quasi-linear. So say on a quiz, you might see an example like this and just say that it's quasi-linear. So look for the plus, but the non-linear portion in one part. Okay. So that's just like a little side note we talk about. This is preferences we do see, but it's not too important. So what we're going to focus on is the next one. This is like the third type, quasi-linear. The fourth we talk about are Cobb-Douglas, though. Now we've already seen this when we talked about derivatives before chapter 1. Cobb-Douglas functions are important, and a lot of times our preferences look more like Cobb-Douglas than what we've seen before, the linear and the Leontief. Remember, the linear and Leontief, these are really extreme cases. For Leontief, they're perfect complements, and we want it in a certain combination. We're not willing to shift our combination. We're not willing to like say, oh, today I'll have a little bit more sugar, or I'll have a different, amount of espresso shots. That's what we're talking about. Here, we want a certain proportion only. Down here, we're willing to substitute them 100% for one another. But sometimes, most of the time in the real world, we're not very extreme. We, might want a certain proportion, but we're okay if it's not the exact proportion. We might be able to substitute between goods, but not perfectly. Things like cooking with olive oil or canola oil. You probably prefer, if you cook, one or the other. You can definitely substitute between them, but they might not be perfect substitutes. So Cobb-Douglas represents these non-perfect substitutes. We can call it, imperfect substitutes, we can say. Just another word for this. Now, this utility function always looks like a constant A times x1, x1 to like the A or alpha times x2 to the beta, B. So x1 and x2 are being multiplied here. There's some exponents. It can be, really any numbers up here, and maybe a constant. Now, I want you to remember, MRS is looking at the partial derivatives divided by each other. So remember, it was mu x1 over mu x2, which was partial derivative with respect to x1 over the partial derivative with respect to x2. Now, when we first did partial derivatives, I asked you to find, something like this, find the partials, and also divide them out. And I did that for a reason, because this is that divided out. So you were technically finding the MRS when we were looking at other functions. I just didn't tell you that. So we also said that there was a trick, and this trick is definitely going to save you time, and you can use it all the time with Cobb-Douglas functions. So only with Cobb-Douglas functions. So I'll say Cobb-Douglas shortcut. when you're looking for the MRS, you can always start off with the first exponent, whatever this is, a, and multiply it by x2, the second variable, which is always going to be x2 for us, times the coefficient here, or I'm sorry, the exponent b times x1, always. And this will always give you the right answer. So it really helps because you're not you don't have to do partial derivatives, right? So this makes life a little bit easier. It's, you have to put some things in, but it's relatively straightforward, I think. So let's just do an example, do it together. U equals 5, x1 to the 0.2, x2 to the 0.7. Again, you want to be able to identify that this is Cobb-Douglas. And it's really x1 times x2 that gives it away. The others didn't have these being multiplied at all. So because they're multiplied, we have Cobb-Douglas. And we can solve for the MRS, which is again the slope of the indifference curve for this. And I'm going to use the shortcut, so that makes life easier. This 5 is actually going to cancel out, so we don't look at that. We use the first exponent, 0.2, multiply by x2, divide by the second exponent times x1. And that is our MRS. If we wanted to, we can divide 0.2 by 0.7, just get a number, possibly decimal, or you can leave it like this. This is the slope of the indifference curve for this function. And you might notice the slope. This is not a constant number. It depends on our values for x1 and x2, right? It's not always going to be one number. And that's kind of important when we look at these indifference curves, and I'll show you what they look like. But always use this trick. Keep that maybe on a note card, and you can solve this pretty quickly without doing a lot of work.
So the x2 would be the 0.2, not the 0.7?
Right. So you kind of use the other exponent.
Okay.
Okay. So the example that they gave in the book, I don't really love it. This is just x1 times x2. It's very simple for a Cobb-Douglas function that a and b terms, both of those are just equal to 1, and that's okay. It's still Cobb-Douglas, and there's, the coefficient just 1 as well. So it's just an easy example. But again, x1 and x2 being multiplied tells us we have Cobb-Douglas. And so the indifference curves for this, kind of these half U shapes. They're not necessarily exactly C's, but they're kind of along those lines, kind of along that possibly. As we increase, go up from, the 0 axis, we get more utility. So like this line that they drew had utility of 25, the next one 64, 121. So if you see a picture like this, where they're not 90-degree L curves, you definitely have Cobb-Douglas. So this isn't too important. Let's look at something. Okay. Now, when we're talking about these Cobb-Douglas functions, or really any of these, we have convex preferences. Now, This isn't too important to know, but I want to show you kind of what it means, and hopefully that makes sense. So again, don't need to know what convex is. It's the shape of the curve, but what it says is that consumers would prefer, when they're looking at these two goods, X1 and X2, kind of like an average for them, like a good amount of X1 and a good amount of X2 they'll be happy with, rather than a lot of X1 and a little of X2, or the other way, a lot of X2 and a little of X1. They kind of want, a good mix of the two rather than one or the other. So they have this indifference curve, Cobb-Douglas, and they have point A, which represents a lot of X2 and just a little bit of X1 at the bottom. And then over here, they have B, which is a lot of X1 and just a little bit of X2. But if we join them together, just draw a line between the two, a point between them, this point C, is going to have a higher indifference curve, a higher utility. So this point C is above this indifference curve in orange. So it is on a higher indifference curve and will give them more utility. They would prefer C to both A and B. Right. So the C is on a higher indifference curve. That's what this idea of convex preferences mean. Again, not too important. Just showing you what it looks like. We prefer not equal necessarily, but a good mix of our goods. We like them, both, and having more of one or the other isn't too much, isn't going to make us too happy. We'd rather a mix of them. Now I'll also show you this. This is a little bit more important. So when we said we're talking about the MRS, it's that A X1 over B X2, technically negative, but again, I ignored it here. I said that it wasn't constant. So it's not a constant number, meaning that depending where we are on the curve, that slope is going to be different. If we are at point A and have numbers for X1 and X2, we can get the slope. And it's going to be different than if we compare it down here. So at point A, this is kind of showing that maybe we have a lot of X2 and not a lot of X1, which is on the bottom. I don't know if you can see that because the controls are there. But X1's at the bottom. We don't have a lot of it. So in order for us, or not in order, but like if we are thinking about getting more X1, one more unit of X1, we're actually willing to give up a good amount of X2 because we have a lot of it. We're like, oh, I don't need all of this. I just want one more X1. But then if we go, say, B to C, get one more X1, we're not willing to give up as many X2s because now we're getting less of them and getting more to like an even bundle. So our MRS goes down as we go down.